Hello and welcome students to your own channel AMPC, where we were discussing electrostatics. So in the previous class we have studied Gauss law and its application, and we did very important questions related to Gauss law. So continuing the same session, in this session also we are going to do only Gauss laws, numericals, or some derivations which are not asked in your CBSE exam, but they are pretty useful for your, you can say that, competitive exams. Okay students, so let us see the question number 1. However, this question is very simple. This question says, consider two infinitely large plane sheets having uniform charge distribution of surface charge density sigma 1 and sigma 2 respectively, placed parallel to each other. Calculate electric field due to them at point. There are three cases students. Point number 1, we can say that left of sigma 1 sheet. You can say that those plane sheets, as I am considering here, is just sheet left of sigma 1 sheet. In between of both sheets. Third one is right of sigma 2 sheet. Okay students, let us see. There are two infinite thin plane sheets and their surface charge densities are sigma 1, sigma 2 respectively, if they have placed parallel to each other. So in this case, the question, in the question, the diagram might or might not be given. So suppose if diagram is not given, then also we can do it very simply. Like what question says that there are two infinite sheets. So students, here it is. This is sheet number 1, this is sheet number 2. Again, there is one simple term you can note down, or you should pay attention, that here only sigma 1 is written. So how can we conclude that it is negative charge or positive charge? So students, if just sigma 1 is given, by default you will consider it as positive. So sigma 1 is given. Another sigma 2 is there. So students, you are saying sigma 2. I have considered that sigma 1 is greater than sigma 2. Okay. This won't change any answer or any solution to this question, because sigma 1 is greater, sigma 2 is lesser. So this is my assumption, and electric field related to that only we are going to calculate. If the condition is vice versa, then a minus sign will introduce in our electric field expression, and minus sign shows that whatever is the direction, the final answer is opposite to it. First we'll do the question, then I'll discuss. Okay students, so if suppose we place two parallel plates, two parallel sheets, so you can think of like this is my first sheet, this is my second sheet, and they are infinite large. So what happened, the left region is this of sigma 1 This is second region, the in between the two plates or sheets, and third region is your right of sheet 2. This is sheet 2, right is that side, so right of sheet 2. Understood? Okay, so for calculating electric field at this region 1, let us say this is region 2, this is region 3. Okay students, so from positive sheet, electric field is radially outward. I'll say this is E1. Okay, so in region 1, electric field due to sheet 1 is E1 equals to sigma 1 upon 2 epsilon naught. So students, this derivation we have done in our previous class, so you can watch a class from there where we have studied the applications of Gauss theorem. Okay students, so E1 is this and the direction is towards left. So since electric field is a vector quantity, so we must write its direction. So E1 is towards left. Now similarly EF due to sheet 2. Similarly due to sheet number 2, you'll say it's E2. E2 will be sigma 2 upon 2 epsilon naught. So second sheet is this. Electric field will be due to that sheet is radially outward like this, and then it will go like this. So E2 is again away from the sheet. So in second region it is the left side, and in first region also it is left side. However, in third region E2 is this students, because electric field are those imaginary lines which moving away normally, moving out normally if there is a positive charge. Okay, so E2 is sigma 2 upon 2 epsilon naught, and its direction is also towards left. So student, what is the net electric field? The answer is they both gets added up. Why? Because the magnitude is there and the direction is same. If the direction is not same, then we would have subtracted it, or we have applied electric field resultant formula that under root a square plus b square plus 2ab cos theta. Okay, so we can write the final answer is, so therefore net electric field in region 1 E1 is E1 plus E2. E1 plus E2. So you substitute both the values, which is sigma 1 upon 2 epsilon naught, sigma 2 upon 2 epsilon naught. So you will get sigma 1 upon 2 epsilon naught plus sigma 2 upon 2 epsilon naught. The students, you will get 1 upon 2 epsilon naught common, and in numerator it is sigma 1 plus sigma 2. So electric field in region 1 is sigma 1 plus sigma 2 upon 2 epsilon naught, direction towards left. So students, this is first part's answer. Okay. The second part says in between both sheets. So in between both sheets, you say if this is a positive sheet, so electric field is in this direction. So E1 is this. Okay. So second part I am writing in region number 2. So in region number 2, electric field due to sheet 1 is E1. Again the magnitude remains same, because for thin sheet electric field is independent of distance. So here electric field due to sheet 1 E1 is sigma 1 upon 2 epsilon naught and its direction is towards right. Towards right. Okay students, so E1 is there. Similarly, sheet 2, E2, the direction is left side. Similarly, for sheet 2, E2 will be sigma 2 upon 2 epsilon naught towards left. Very simple. So what is net electric field? So therefore net electric field will be E2, second region will be, see students, first electric field is, sorry, first is right side, second is left side. So actually we will subtract the magnitudes. We will subtract the magnitude. So E1 minus E2. And I have told you now, I have considered that sigma 1 is greater than sigma 2. That is why we are subtracting a smaller quantity from the bigger quantity. A smaller quantity from the bigger quantity. So my direction will be towards right. Okay, if you have considered the opposite thing, so in that case your final answer is towards left. So both the answers are correct. Okay students, so from here I can say, if I have substituted the values, this is sigma 1 upon 2 epsilon naught and minus sigma 2 upon 2 epsilon naught. This is your E2. So I have considered sigma 1 is greater, that is why from larger value I have subtracted a smaller value. So the answer is towards, you can say that right, towards right. Okay students, so this is part 2, towards right. If the student will consider that sir sigma 2 is greater, so in that case you write sigma 2 minus sigma 1 and your direction is towards left. Okay students, for the third case is very similar. Third case is saying right of sigma 2. So right of sigma 2 is this sheet. So students, you write this E1, E2. So in region 3, similar to region 1, both the fields are on the right side. In region 1, both the fields are on the left side. So your final answer is E3. Both the fields get added up to epsilon naught and the final answer or final direction is towards right. So students, our final answer is this: first part, second part, and here is your third part. Okay, you can note down. This is very important question. Okay, students. So you can pause the video and note down. Okay. Okay. So next question. In the next question, a very simple term is there. Again, two sheets are there. And this question is a formation of capacitor. Our next class would be based on capacitor, that what are capacitors and how they are formed. So students, very simple question. What I am saying here is that again, two sheets are there. One is having plus sigma 1, another is having minus sigma 2. One is having plus sigma 1, another is having minus sigma 2. Again, you have three regions. So the question is same. You have to calculate electric field in all three. Very simple. Okay. See. In region 1, however, the second sheet is our second sheet is having negative charge. So students, minus 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 minus. Again I have considered that sigma 2 in magnitude is lesser than sigma 1. Okay, they might be equal or sigma 2 is greater. So it depends upon the condition. if we have calculated for a basic thing, then we can substitute sigma 1 equals to sigma 2 and we can calculate a final answer. Okay students, so from here, for positive charge, all the things remain same, but for negative charge, things gets changed. Because you have studied that a negative charge, or for negative charge, electric field lines are terminating at negative charge and they are normal to the surface. So students, for negative charge, lines are moving like this. For negative charge, lines are moving like this. Towards negative, they are terminating. So consider these two lines as a single line. However, the region gets divided, so I have drawn in two different parts. Okay. So this red one is your E, second plate E2. This is E2. This is E2. So from here students, we can see that E1, E2 in region 1, now they are not in same direction. Now they are in opposite direction. So I am just writing the final answer. In region 1, you can do this question in a similar way. However, if you face any doubt, then you can comment below and definitely in that case I will discuss. Okay students. So here E1 you would say it is sigma 1 minus sigma 2 upon 2 epsilon naught. In region 1 they get subtracted. In region 3 also they get subtracted, which is E3 sigma 1 minus sigma 2 upon 2 epsilon naught. The direction is right, the direction is left. And in region 2, previously they are getting subtracted, now they will be added. So students, your E2 will be sigma 1 plus sigma 2 upon 2 epsilon. So I hope so you have understood this second question also. So how capacitor are made up of? So students, in capacitor sigma 1 equals to sigma 2. So in that case, those two fields become 0, 1 and 3 become 0. Only in region 2 there will be a field. So students, this is a very important question related to your CBSE boards as well as your competitive exams. Okay students. So now we are doing next question. Okay. Next question is okay students. So our next topic is some derivation related to electrostatic potential energy. Okay students. So electrostatic potential energy, if we are bringing just a one charge Q1 from infinity to a particular point, in that case no work is done. So your electric potential energy is 0. So previously we did one question that suppose there is one isolated point charge is there. So what is potential energy of the system? You will say sir 0. Instead of one isolated point charge, suppose there are two charges. Okay, so what is the work done? Work done will store as electric potential energy of a system. If there are three isolated point charges, so for installing three charges, what is the net work done? You have done this. However, this question is quite easy. But today we are doing one derivation which is very important for your competitive exams. In CBSE this might ask or might not ask. Okay, so our heading is electric potential energy due to a uniformly charged thin spherical shell. Okay students, so spherical shell means a hollow sphere. So in this derivation we can say that consider a sphere of center O and radius R. You can think of a plastic ball, or you can think of this. So this plastic ball is empty, this ball is empty, hollow, nothing is inside this ball. So radius is R, and this shell is having uniformly charged. So suppose a Q charge is there, suppose capital Q charge is there, suppose capital Q charge is there, which is uniformly distributed over the surface of a spherical shell. Okay, so you can think कि initially the shell must be uncharged, and then slowly and gradually we are bringing small dq to this particular sphere. So I am saying that initial charge on that sphere is 0, and final charge on that sphere is Q. So what you are saying in that case is, suppose this shell is uncharged, you brought very small q amount of charge to it, then again q plus dq, then again q plus dq. So a particular time a potential is there, and electric potential energy we have already studied that it is related, or sorry, it is denoted as U, and U is always, students, it is W. W is a work done, and work done will be integration dW, and your dW is V dq. Okay, so your integration is V dq. This is just a simple blueprint, or you can say a brain map for solving this type of questions. Okay, so the previously what I was saying is, suppose there are 3-point charges, that question is also done by this. So dW is V dq. Okay, so this is your electric potential energy. So students, suppose there is 0 charge. So for bringing a small dq, there is no work is done. But I am saying, let at any instant the sphere having Q charge, it should be in the same line, so you can continue in the same line. Let at any instant the sphere is having a small q amount of variable charge. Okay students, this is also a notation that if I have written a capital Q, then it is a constant thing. If I have written capital R, then again it is a constant. But if we are saying that a small q or a small r like that, so those terms used to be variable terms. Okay students, so suppose a q charge is there, so like some charge is missing, so q, which is lesser than capital Q. So potential is therefore electric potential will be very simple. It is 1 by 4 pi epsilon naught Q upon R. This is potential related to a sphere. Whether this sphere is hollow or filled, answer does not matter. The potential is kq upon R, where k is 1 upon 4 pi epsilon naught. So students, electric potential is this. Okay, for bringing dq extra, charge on the sphere, amount of work done will be, for bringing very small charge, small work done will be there. So dW will be V dq. You know the value of V. V is your potential. Let us say it is equation number 1. So this was our blueprint. I am erasing that. Actually, that part you should not write in the derivation. But whenever you see this question or these types of question, that blueprint must strike in your mind. Because generally what students used to ask from me is, sir, how can we conclude that this type of derivation should be done? Okay, so there is always keyword. So here keyword is electric potential energy. So students, energy is always work. So in this way you can remember this thing. Okay. So dW is VdQ, or I can write dW is V is this kQ upon R, 1 upon 4 pi epsilon naught Q upon R, and there is dQ. I have written this thing from equation number 1. Very simple. This is your work done. So what is your net work done? Therefore, net work done in bringing charge up to Q from initial is 0. Okay. So net work done is W will be integration dW. So I am substituting the values. So the values are integration 0 to Q, dW is this 1 upon 4 pi epsilon naught Q dQ upon R. So students, 4 pi epsilon naught is constant, universal constant. We can take out of derivation and integration, and then R again it is constant. So it is also taken out of integration. So 1 upon 4 pi epsilon naught R, and then integration Q dQ. You all know that x dx is integration is x square upon 2. So our final answer would be 1 upon 4 pi epsilon naught R Q square upon 2, limit 0 to Q. So substituting the values of capital Q minus 0, we get 1 upon 4 pi epsilon naught R Q square minus 0 square upon 2. This is your work, students. So you will say this work will store as electric potential energy of the system. So this work will store as electric potential energy of system. So work is your U. So U will be 1 upon 4 pi epsilon naught Q square minus 0 would be nothing upon 2R. So students, 2 you can shift it here. So your final answer is 8 pi epsilon naught R, and I am writing it as directly Q square upon 8 pi epsilon naught R. This is your electric potential energy due to a uniformly charged thin spherical shell. Okay, students. So see, if it is a thin spherical shell, so nothing must be inside it. So it is a spherical shell. So students, spherical shell, you have to imagine that spherical shell having charge on its surface only. But if it is a, instead of thin spherical shell, if it is a solid sphere, again in Gauss law we read solid sphere, and that solid sphere was non-conducting. Then non-conducting. So then from giving 0 to capital Q amount of charge, the entire charge is not going to be concentrated on its surface only. Some charge may get inside, some charge may get outside, and again if it is the charge is inside and outside, then again potential will not be a constant, since the radius is also variable. So integration becomes slightly different, but the integration again would be very simple, because how we can treat it as, suppose if there is a sphere if there is a sphere at particular instant, it is having capital Q amount of charge. So starting from zero, again slowly the radius will increase. You can consider this in that practical form. We can say, suppose this is one hollow spherical shell. Again there is another hollow spherical shell, another hollow spherical shell, another hollow spherical shell. Starting from zero radius, we reach to capital R. So a number of shells will make a solid sphere. Understood? So we are doing the same. Okay. Next. Okay students, see, suppose at instant the final charge is capital Q. So the charge must distributed inside the shells also. You know the shells? The inner part of the sphere. So suppose this is center O. So in that case, we'll say, consider rho is a volume charge density of given sphere. Right? Now we'll say consider small, or we can say consider a sphere of radius r less than capital R, of radius r less than capital R, then before potential, then charge is stored inside the sphere is, you can say Q. So students, Q will be volume charge density, charge density into effective volume, What is this? You have to understand this thing. Suppose I am saying up to that region only I have brought Q charge. So how much charge is inside that sphere? So how much charge inside that sphere of radius small r? I am saying that Q would be volume charge density into effective volume. And what is volume charge density? It is total charge upon total volume. So students, we can write Q equals to, not sigma, it is rho into effective volume, volume of this red shell or sphere. So that would be 4 upon 3 pi small r cube. And a volume charge density of this given sphere can be written as rho equals to charge upon volume, 4 upon 3 pi r cube. So you can substitute this value over here. So small q is given by, so therefore small q comes out to be, rho is q upon 4 by 3 pi r cube into 4 by 3 pi r cube. 4 by 3 pi gets cancelled out. So q comes out to be q r cube upon r cube. Okay, this is your charge. Okay, so next is potential. So therefore potential due to charge q. In the same way, students, we can write potential is kq upon r, what previously we have written. K is your 1 upon 4 pi epsilon naught q by r. Okay, as previously r was a sphere, the full sphere, so you have taken it as capital R. Now you are writing for only small sphere which is having charge q. That red one is having charge small q, so you are writing small r. Very simple. Okay, consider it as equation number 1 was this. So from 1, now 2 is this. So from 2 I am substituting the values. Make a line. Okay, now you won't get confused. Okay students, V will be 1 upon 4 pi epsilon naught. Q is from equation number 2. Q r cube upon capital R cube. Okay, you have written, and again one small r is also there. So you have written from equation number 2. Okay, so r get cancel out and you will get 4 pi epsilon naught q r square upon r cube. No, there is a mistake. That was a small q, that is capital Q only. This is correct. So your potential is this. You'll say for giving extra charge dq. Students, you have remember now, we are calculating electric potential energy. Electric potential energy is work only. Work is V into dq. dW is V into dq. So work is integration of dW, which is V into dq. So we have found V of this red radius, and then we'll find dq. V into dq will be small work done, and integration will be the answer. Very simple. Okay, see, for giving extra charge dq, we need to increase the radius from r to r plus dr. See student, we have already covered that much of region, a very thin spherical shell. As we have discussed, I have shown you now that very thin shells will make a solid sphere. So very thin, this one dr. So this region stores dq amount of extra charge. Okay, so again dq will be like this only. So r to r plus dr. So therefore dq equals to volume charge density into small volume. Small volume, students, it is sigma. From equation number 1, I will substitute the values, which is q upon 4 by 3 pi r cube, and small volume of this red region. So again, this is a sphere, so you can write 4 pi r square. So surface area is 4 pi r square. Surface area of this red sphere, and then the thickness is dr. So 4 pi r square dr would be the term. So student, 4 pi get cancel out, 3 will move upwards. So dq will be, so from here you will say dq, make this equation number 3. So from here dq will be total charge, 3 will move upward, 3q, here r square dr upon r cube. This is your dq. So small work done for dq charge is dw equals to v dq. So therefore total work done will be W equals to integration dW. W will be integration dW. Okay, and here we are integrating shells. So we'll integrate from radius is 0 to capital R. So students, after substituting the value, total work done, W will be integrating V dq. V is V dq. Okay, so V is from equation number 3 and 4. From equation number 3, V, and dq is 4. So V will be 1 upon 4 pi epsilon naught q r square upon r cube, and then dq will be 3q r square dr upon r cube. Here you will write in bracket. Here you will write in bracket from 3 and 4. Okay, so you can write this term in bracket from 3 and 4. We have substituted this, and after solving, integration limit is also there. Integration from 0 to capital R. So W will be integration 0 to capital R. Here it is 3q square. R into R square into R square will be R power 4, and then dr division 4 pi epsilon naught R ki power 6. Division 4 pi epsilon naught R ki power 6. And the integration. So there are terms which are constant. So constant will take out of the integration. Only the variable terms are r square into r square is R ki power 4 into dr, and limit 0 to r. Very simple. And now integration of r ki power 4 or x ki power 4 into dx is x ki power 5 upon 5. So you will get 3q upon 4 pi epsilon naught r ki power 6 into r ki power 5 upon 5. Limit 0 to r. So in the next line we will say it is 3q 4 pi epsilon naught. 4 5s are here. 4 into 5 will become 20. 4 pi epsilon naught. So 20 pi epsilon naught r ki power 6, and in the bracket r, instead of r we will put upper limit minus lower limit. So r ki power 5 minus 0 ki power 5 divided by 5 we have already taken up, which made this term 20. So student, here r ki power 5 and denominator r ki power 6. So I am writing here 3q upon 20 pi epsilon naught r. Because r ki power 5 in denominator r ki power 6 they get cancelled out. This term will remain. So student, this is your work. Now you will say this work will store as electric potential energy of a system. This work will store as electric potential energy of a system. So I am writing it here. So I am writing the final expression here. U will be W is 3q upon 20 pi epsilon naught r. 3q square. Student, by mistake a square is there. Otherwise it is dimensionally wrong. Square. So 3q square. So this is your final term. So due to a solid sphere, potential energy is this. This derivation is very important if you understand in this way. Okay. So this is your okay. So student, next part is related to that only, which is earthing of a conductor. Okay students, so very important topic, earthing. However, questions directly related to earthing has not been asked, but in case of electrostatic induction charging, or even in your next chapter, which is current electricity, again you are going to study earthing only. So earthing means, or the symbol of earthing is this. This you have previously studied in your smaller class or in class 10th. So students, symbol of earthing is this. And for understanding earthing, it means charges transferred to earth. Here, if we consider our earth, so students, earth is a good conductor of electricity. Earth is a good conductor of electricity. So whenever there is an excess charge, it will move or it is transferred to the earth. So the excess charge, the process of charges transferred or the excess charge transfer to the earth is called earthing. Okay. So when we earth any object, so what we used to do is, actually, since earth is a good conductor of electricity and the potential of earth, we can say that the formula is kq upon r. So students, what is the radius of earth? Or as compared to this sphere, a very small sphere. So as compared to this very small sphere, what is the radius of earth? You can say, sir, it is 6.4 into 10 to the power 6 meters, which is very huge. As compared to this sphere, the size of earth is very huge. So if radius is, you can say that very huge or infinitely large, so the potential becomes zero. So students, you can say that the potential becomes almost zero. So what is the potential of earth? It is almost zero. Okay. So next is, what is the amount of charge on the amount of charge, we can consider it as to be very small, or we can say it is zero. However, it is negative of 1 nanocoulomb per meter square, which is very small. You can say that Q is very small, R is very large, so potential of earth is zero. Okay. So earthing means whenever the excess charge is there, it is transferred to the ground. Okay. So you can think, suppose there is a sphere. If a negative charge, or no, not negative, suppose the sphere is neutral. Suppose the sphere is neutral and a positively charged rod is brought near. So negative charge induces, this process is called as electrostatic induction. So negative charge induces on the left side and positive charge induces on the right side. So in the sequence of diagrams, the process of earthing means I have connected this device to earth. Okay, so all the excess charge is grounded. Okay, so now understanding earthing once again, that excess amount of charge will be grounded. Okay, you all have seen the example of earthing in your houses. We have seen that there are three plugs in your switchboard. So in electrical switchboard, there are 3 plugs. They are like this. Okay, and you used to put charger inside this plug. Okay, so students, this is your plug. So one is positive, another is negative. So one positive and negative are coming from electric board, like the company which is supplying electricity to us. And the third, which is put upward and having a larger radius. Again, the third one is having larger area, larger radius. And why this is so? Again, there is an important concept we'll study after Ohm's law. Okay, so why this is having larger radius? However, this larger radius is further connected to a wire, and the wire is connected with a metal plate, which is put inside the earth. This process is called as earthing. So in that case, suppose some extra charge coming on the surface and or some extra charges coming on the live wires, then because of earthing wire, that excess charge will be grounded. Again, earthing also means as grounded. So that excess charge is grounded. Understood? So that excess charge is grounded. If the earth connection is not there, then we might feel those charges in the form of electric shock. So in that case, we might get electric shock. So what is the need of earthing? I hope so it is clear. Okay students, so that was again a very important topic. However, we have not left any topic related to our JEE mains or CBSE. We have done all the topics up to chapter number 1. Okay, so related to that or related to those energies, we are doing one question. The question is, however, very simple. You can say that suppose there are 3 spheres. So students, I am writing the question. Okay, before writing, I am thinking that I have made one assignment for you. This assignment is related to JEE only. Very good questions are there. So from that assignment, we are doing that question. The assignment PDF is shared in the link is shared in the comment section. You can easily download that question. Okay. So see, there are 3 spheres. 3 concentric spherical shell. 3 concentric spherical shell. Shell A, shell B, shell C. Okay. Shell B is grounded. Okay. And in shell A is having, you can say that radius A. Shell B is having radius B. Shell C is having radius C. Okay, and what else is given to us? That suppose A shell is having a Q amount of charge. So charge Q is given to a sphere A. So I am writing this as a small q, students, a small q, and minus q is given to the outer sphere. Question is saying calculate charges induced on the inner as well as outer surfaces, charges on the inner as well as outer surfaces of the sphere. As we previously did, कि suppose a small q charge is there, and if it is a cavity or if it is a solid sphere, solid conducting sphere must be conducting sphere, so the entire amount of charge will move outward. However, those 3 are the shells, radius are given. Question is saying what is the final amount of charge. Okay students, so see here q is there, q amount of charge is there, so minus q will induce, minus q will induce over that surface. Now the outer surface is having, however same amount will not come, so q dash is there, and minus q dash induced to the inner surface, and at the outer surface it would be, it would be q dash minus q. I am repeating the charge distribution again. Q charge is there, so minus q charge, so minus q charge will induced in the inner sphere, inner surface of B. Okay students, I should not write C at this point because here it is mixing up with the first name of the sphere. Capital B is the second sphere, so inner surface is this. Some amount of charge gets grounded because from question I can conclude that VB must be 0. Okay, from a sphere, from this question, this symbol is Earth, so VB must be 0. So now a small q, some amount charge gets grounded, so some positive q dash remain on the surface, so that the potential becomes 0. If this surface is having q dash, so minus q dash will induce on the inner surface of C, and outer surface gets plus q dash. And since previously it is having small q, negative amount, small minus q amount of charge is there, so total charge according to additive property of charges, so additive property of charges will say q dash minus q. Okay, so now what we'll do, we'll write the potential of all the surfaces. So after distribution of charges, I'll say potential of B sphere B. Okay, due to charge on smaller surface A. So there are actually 5 charges, students. So what are the 5 charges? This Q and minus Q was given. However, due to induction, number 2, then number 3, then again due to induction, number 4 and number 5. So this minus Q is replaced by this. So what is potential of B? Potential of B due to sphere A. The total charge is Q and the radius and the sphere B is having radius small b. So potential is, we can say that V1 would be kq upon r. So 1 upon 4 pi epsilon naught q upon radius is b. Okay. Now potential of B due to sphere A is done. So sphere B inner due to inner surface of B will be V2. B inner surface is having minus q amount of charge. So student, it is minus 1 upon 4 pi epsilon naught q upon B. Now due to outer surface of B, you will say, sir, it is V3 and outer surface is having q dash amount of charge. It is not equals to minus q is plus q. It is not equals to plus q because some amount of charge may get grounded, because sphere B must have zero potential. From the question we can conclude this. So students, V3 is 1 upon 4 pi epsilon naught q dash upon radius is B. So now potential of B due to inner surface, number 4 is inner surface of sphere name is C. It is, students, V4 will be minus q dash upon 4 pi epsilon naught C. Okay, and the last is due to outer surface C, V5. V5 would be q dash minus q upon 4 pi epsilon naught C. There's a done. So there are 5 different potentials. So what is the net potential of B? So therefore, net potential of sphere B, net potential of sphere B will be, VB will be V1 plus V2 plus V3 plus V4 plus V5. Okay, I am taking 1 upon 4 pi epsilon naught common. I am taking 1 upon 4 pi epsilon naught common. Now see, 1 upon 4 pi epsilon naught I have taken common. For the first surface it is q upon b. Q upon b. For the second surface it is minus q upon b. For the third surface it is q dash upon b. For the fourth surface it is q dash upon c minus q dash upon c. And for the fifth surface it is q dash minus q upon c. Understood, students? From here we'll say that those terms get cancelled out. However, q dash upon c and q dash upon c also get cancelled out, but we'll write in another line. So from here I am saying that it is 1 upon 4 pi epsilon naught q dash upon b plus, not plus, it is minus q dash upon c, then plus q dash upon c and minus q upon c. Now they also get cancelled out. So VB comes out to be 1 upon 4 pi epsilon naught q dash upon b plus, no, not plus, it is minus q upon c. Understood? This is potential of B, net potential of sphere B. Now we'll say, since sphere, yeah, we can say that shell also, since sphere B is grounded connected to earth, earthing. So therefore VB must be 0, and VB is this, very simple, 1 upon 4 pi epsilon naught Q dash upon B minus Q upon C will be 0. 4 pi epsilon will go there, and after solving, what we get? So after solving, what we get? 4 pi epsilon get cancel out. Q dash upon B equals to Q upon C. So from here Q dash will be QB upon C. So now we are drawing the final charges. So therefore final charges are shown below. Now final charges: sphere A, sphere B, sphere C. A, B, C. B is grounded. Okay. So now A is having, I am writing with a red pen, A is having Q charge, B inner is having minus Q charge, B outer is having Q dash. So students, Q dash is QB upon C. Now you understood, some amount of charge is grounded. Okay, so this Q dash is always lesser than, this Q dash is always lesser than Q. Why this is so? Because B is smaller than C. From the diagram you can see that. Okay students, so QB upon C is here. So from here you will say it is minus QB upon C, and for the outer surface it is QB upon C minus Q. You know, Q dash minus Q. So Q dash was QB upon C minus Q. So it is having total negative charge only. So there is a final answer, and you can note it down. So this is a method from which we have calculated the amount of charges on different surfaces. Okay. So after this, if I say, do we had another method for calculating charge? So my answer is yes, and the concept we'll use is Gauss law. Okay. So next question is this only. So we'll say. Okay students, so related to that only, this is the question number 2 of my assignment which I have shared below. Okay, so what question number 2 says, that there are 2 infinite metal sheets. In the beginning also we did the same. However, these sheets are not thin, they are thick. Okay, so there are 2 infinite metal sheets. One is having Q1 amount of charge, another is having Q2 amount of charge. So question is asking, if they are placed parallel to each other, then what is the charge on all the 4 surfaces? So actually students, there are 4 surfaces. You can say that this is number 1, this is number 2, this is number 3, this is number 4. There is a thick metal, so this is a metal. Now there are 2 surfaces, one is above and second is below that. However, the size or the length of this metal or this sheet must be very large. Okay students, you understood? So from here I can say that, suppose minus Q amount of charge is induced on the upper surface of B. So total charge must be Q2. So plus Q is on that surface, and total charge is Q2 plus Q. So the total charge is on that surface is Q2 plus Q. Similarly for upper surface, if this surface is having minus Q, so due to induction, this surface must be positive Q. They must be equal and opposite because none of the plates has been grounded as we did in our previous question. So Q is there. So minus Q must induce on the upper surface, and total charge is Q1. So this surface is having Q1 amount of charge. Okay. So moving forward. So students, for solving this, consider an imaginary Gaussian surface, because it is always easier to consider something equivalent to 0, because substituting any value equivalent to 0 is very simple. So those rods, both the rods or both the sheets, thick sheets, are made up of metal. So I am saying consider a point P inside a metal. And we know that inside a metal there is no electric field. So at point P I am writing electric field by using the concept of thin infinite sheet, plain thin infinite sheet according to Gauss law. So I am saying at point P, electric field due to Q1 minus Q surface, Q1 minus Q surface will be, you can say that electric field is sigma upon 2 epsilon naught. So students, you can say that the A is the area. So you are saying Q1 minus Q upon 2 epsilon naught. So electric field, student, it is sigma upon 2 epsilon naught. So sigma is Q1 minus Q upon A. I have considered that red one area equals to A, and the direction is downwards. Okay, even. Very simple. Huh? Nothing difficult. This is downwards. If a positive charge is upward, so positive will repel, so downward. Another positive charge is downward, so it will repel. So downward charge will repel upward. So similarly, due to plus Q surface, E2 will be Q upon 2A epsilon naught. It is upwards. Okay. Now third surface is having minus Q charge. So minus again will attract. So it is downward. So and due to minus Q surface, you can mention it as third surface also. I am saying E3 will be Q upon 2 epsilon naught A or 2A epsilon naught. It is downwards. And the fourth surface is this. And due to Q2 plus Q surface, we will say E4. It is Q2 plus small q is variable, 2A epsilon naught upwards. The student, you can understand it this way, that here Q2 plus Q, where small q is a variable charge. We have to calculate that what is the value of q, because question says Q1 and capital Q1 and capital Q2 given to us. So I have considered that positive or negative q is induced here. So the net charge on the upper plate is capital Q1 and on the lower plate is capital Q2. So I have written all the four surfaces having that much of electric field. So what is the net electric field? So therefore E net will be E1 minus E2 plus E3 minus E4 mod, because of directions. And E net comes out to be E1. Okay students, 2 epsilon naught A, 2A epsilon naught is common. 2A epsilon naught is common. So I am taking LCM as 2A epsilon naught. From here we are getting Q1 minus Q. Next is minus Q. Next is downwards. Downward I have taken as positive. So which is plus Q. And again upward is taken as negative, which is minus Q. Minus Q. Okay, however, I should write like this. And if we open the bracket, so however we should write like this. But after opening the bracket, we will get, so after opening the bracket, we will get minus Q2 minus Q. Okay students, Q get cancelled out. Now minus Q will become 2Q. So electric field comes out to be E net at point P. At point P. Remember students, P point is inside the metal. So it is Q1 minus 2Q. Before that Q1 plus Q2 minus 2Q upon 2A epsilon naught. Since E net is 0, so implies Q1 plus Q2 minus 2Q upon 2A epsilon naught must be 0. From here, Q1 plus Q2 equals to minus 2Q. So Q comes out to be Q1 plus Q2 upon 2. Very simple. So what is the amount of charge on all the four surfaces? So I am writing the final answer on the diagram itself. You can again solve. Solve on your own. So Q1 is subtracting by this. So upper surface is having Q1 minus this. So student, you will get Q1 minus Q2 upon 2 after substituting the value of Q. Okay. Next, plus Q is there, which is Q1 plus Q2 upon 2. Third surface minus Q1 minus Q2 upon 2. Okay. And for the fourth surface, Q2 plus Q. So Q2 plus Q. So this thing comes out to be. And the final surface would be. Actually, there is a little mistake. So we should check the previous one. All those are random errors. Happen sometimes. So we can commit mistakes. That's fine. I just found it. Actually, students, see from here it is Q1 minus Q and here it is minus Q2. So it's my bad. We have to write minus Q. That is why this thing sometimes happens. Minus Q. So you get minus Q over here. So small q is Q1 minus Q2 upon 2. Now we are going to solve. So small q minus this. So if minus Q is substituted over here, so we get Q1 plus Q2 upon 2 on the upper surface. For inner surface it is Q1 minus Q upon 2. For this surface it is Q2 minus Q1 upon 2. And for the outer surface, if I substitute the value, again I get Q1 plus Q2 upon 2. So students, these are the four answers. This is first surface, this is second surface, this is third surface, and this is fourth surface. So there are four surfaces, 1, 2, 3, 4, and those are the respective answers. Hope you understand this. However, this type of mistake sometimes happens. Okay students, so that's all for today. However, you can do all the questions which I have shared below in the link, and we can discuss those questions in our next lecture. Okay students, thanks for watching.